Hi everyone, my name is Jun Yu. This is a video project for the course ESE 523. Today I'm going to introduce you a cutting-edge quantum computing platform, neutral atom arrays. This approach has been gaining serious traction recently and could play a central role in the future of quantum computing. On the right-hand side of this slide, I have shown a graph for the rubidium atoms. It has two states, the ground state G and Rydberg state R. And this can be treated as the 0 and 1 in a qubit system. Why are neutral atoms so exciting for quantum computing? There are several key reasons. The first is that they have high scalability potential. We can trap and arrange hundreds or even thousands of atoms using optical tweezers. These are highly focused laser beams that act like tiny tractor beams for individual atoms. And each atom state can be easily identified. If it is present in this picture, it is in the ground state. If missing, we can treat it as being a Rydberg state. The second reason is that this platform has flexible qubit connectivity. Researchers can move these atoms around to make the qubit connection and achieving control gate like CZ. And the third reason is that these systems are surprisingly stable, and we can operate them at a room temperature, which is a huge practical advantage over platforms like superconducting qubits or quantum dots that require dilution refrigerator. Now we are going to introduce the applications of the neutral atom platform. The first application is analog quantum computing. This is where we engineer a quantum system using the natural physics of neutral atoms to directly simulate other complex quantum systems. So here is the Hamiltonian of the Rydberg arrays. And this Hamiltonian is extremely clean and easily to control. It can be used to simulating physical models and solving optimization problems. For example, on this picture, I show an example that's solving the maximum independent sets problem using the QERA's Aquila device. On the other hand, we also have digital quantum computing, which uses quantum gates just like we see in the superconducting or quantum dot systems. What's exciting here is that neutral atoms have achieved a very high fidelity physical operations, and we are now scaling up to logical qubit systems. For example, the Harvard group have achieved 48 logical quantum processors last year. Now we are going to compare the neutral atom device with other quantum platforms. The neutral atom device have a high performance over all the metrics. It has a high scalability potential. It can easily scale up to hundreds to thousands of atoms in the device. The commercialized quantum computer Aquila from QERA, they have 256 qubits in their device, and they have a high gate fidelity. The state-of-the-art gate fidelity for the 2-qubit gate in the neutral atom device is around 99.5%. And also they have a very high flexible connectivity. The items can be moved around and making flexible connection. They are operating in a room temperature and easy to fabricate. Compared with the neutral atom, the superconducting device are suffering from the connection problem. Their connectivity on the device are highly depends on the position of these qubits. And also they using a dilution refrigerator to cooling into the low temperature. For the quantum dot, they are believed to have a high scalability, but the fabrication for this quantum dot is very difficult. So usually they only have tens of qubits in their system, and they also suffer from the connectivity problem, and they are operating in a low temperature. And for the ion trap, they are suffer from the scalability issues, and they are kind of difficult to fabricate. Now let's take a look at how this field has evolved. In 1990s, researchers laid the foundations for the neutral atom quantum computing and proposed the concept. By the 2000s, optical tweezer technology enabled the trapping and controlling single atoms with focused laser beams. In 2010s, these technologies scaled up, forming controlled arrays of tens of items in 1D and 2D, along with high-fidelity 2-qubit gate using the Rydberg blockade. Then, around 2020 and 2022, the field commercialized, with companies like QERA, Pascal, and Iton Computing emerging. Finally, by 2023 to 2025, groups such as Harvard are aiming for fault-tolerant and universal neutral atom processors, pushing beyond 48 qubits. This is an exciting, rapidly advancing journey. Now we are going to introduce the device control of the neutral atom device. The first step is the item loading process, which is the initialization of the quantum device. So here is a picture of the Rydberg device. It has three areas. On both sides, the rectangular areas are called the reservoirs, and in the middle is called the computing area. So the initialization process is using the optical tweezers that moving the items in the reservoirs to the computing area. Notice that all the items are prepared in the ground state because they are shining. The second step is the coherent control. Here, I show the Hamiltonian of the system. It has three terms. On the left-hand side is called the Rabi oscillation terms, which govern by the amplitude omega depending on t. In the parentheses, we have an operator related to the ground state and Rydberg state. So using these kind of operators, we can achieve the resonant Rabi oscillation as shown in the pictures. Notice that there are some special cases. For example, if we set the phi equals to 0, the terms, the operators in the parentheses becomes the gr plus rg, which is the sigma x operator. If we choose the phase phi as pi over 2, this operator becomes sigma y operator. And in the middle, the delta times ni is a detuning operator that can detune the Rabi oscillations. On the left-hand side is called van der Waals interaction or multi-qubit interaction. It's governed by constant Vij. This constant Vij is determined by the positions between the items. So here is the expression of Vij. Notice that if the two items, for example item I and item J, are very close, the Vij should be very huge. So this can be a very huge energy term. By having this large energy, we will observe some physical phenomena, which is called Rydberg blockade, which means two items that are very close cannot be in the Rydberg state simultaneously. And researchers using this kind of phenomena to create 2-qubit gate like CZ gate. Now, after talking about the coherent control, we can talk about the measurement. So the measurement of the Rydberg device is no more than taking a picture of the items. If the items are shining, which means they are in the ground state, and we using 1 to represent them. If they are missing, so they are in the Rydberg state, so we use 0 to represent them. So we can read out the quantum state from this picture. Finally, we are going to talk about the challenges and the future development of the Rydberg device, the neutral atom device. Despite the huge progress and high performance in a lot of metrics like the scalability and gate fidelity, there are still a lot of major error sources in the neutral atom device. For example, the item loss, which means you will lost the item when doing the computation, and also you cannot move your item very fast because that will cause error in the device and lower the gate fidelity. However, the researchers still have a very clear picture for the future development of the neutral atom device. The first step is the quantum error correction. There are a lot of quantum error correction code like toric code, LDBC code designed for neutral atom device that may correct the errors that I mentioned before. Also, researchers plan to scale the system to more than 1,000 logical qubits with a very low logical error rate at around 10 to the minus 6. With this upgrade and exploration, I think finally people can find real applications that run on this neutral atom device and make impact to the physics, chemistry, and optimization. Thank you so much. This is all the things I need to present today.